Greetings, everyone. I see that people are joining us from wherever you are. Happy St. Patrick's Day. And we'll just give people a few extra minutes here to join the webinar. We have a fantastic webinar for you today. And so just sit tight and we'll be back with you in just a minute or so. And while you're waiting, I several times you'll hear me promote the IWCS Cable and Connectivity Industry Forum that takes place in September. It's a little early this year, but it's in Orlando, Florida, and we hope you'll come and not only get a lot from the IWCS conference, but maybe you'll have a moment to go over to Disney and see some of the new rides. Some very exciting stuff going on over there. But please, if you haven't already, consider submitting an abstract. The abstract submissions is open for the next 3 weeks, and we hope that you and your colleagues will put in a presentation for a technical paper and put it in an abstract. So again, just another 30 seconds or a minute. I still see some people joining. All right, well, why don't we go ahead and we'll get started. There will be some last minute folks joining us, but again, greetings, happy St. Patrick's Day from wherever you are. We appreciate you joining us, and I guess I should say good evening. I see folks joining us from Asia, and good afternoon and good morning. Welcome to today's IWCS webinar. My name is Dave Cadu. I'm honored to be your CEO and director of IWCS, and I'll be your moderator for today's event. A few housekeeping items, just so you know that as an attendee, you're part of a larger audience, and so you'll be participating in listen-only mode. As a reminder, this event is being recorded for rebroadcast. We encourage you to submit written questions at any time during the presentation. Please use the chat panel. You can see the chat button at the top of your screen typically. And after typing your questions in the space at the bottom, hit the send button and your questions will be addressed as time permits at the end of the presentation. Our webinar series is being hosted by the Cable and Connectivity Industry Forum, and as I mentioned a few minutes ago, we're excited to be putting together our 2023 Cable and Connectivity Industry Forum that takes place in September in Orlando, Florida at the Gaylord Palms. And we hope that you'll be submitting an abstract or invite your colleagues or supply chain partners to submit a technical paper so we can have a very strong and robust program this year. So today we welcome Xiaosong Wu. Xiaosong has been a consistent contributor and presenter at our IWCS conferences. Xiaosong is with Covestro. He's a senior scientist, and he's located in Illinois, USA. Xiaosong will be presenting his paper on the next generation optical fiber coatings with both improved tear resistance and superior microbending resistance while maintaining robust draw processing capability. Dr. Xiaosong Wu is currently a senior scientist of the Fiber Optic Materials group at Covestro. He holds a doctorate degree in Photochemical Sciences and has been in various research and development positions throughout his career. So Xiaosong, we welcome you today and thank you for presenting this important paper. And we look forward to hearing your comments.
Thank you, Dave. You can hear me okay, right?
Yeah.
Okay. All right. So first thing first, we would like to thank IWCS for the opportunity of sharing our latest innovations in today's global webinar. It is quite remarkable that despite of all the challenges in the recent years, IWCS is always there and all here to pull the global community together. For example, this is the starting time for today's webinar. It lists the time for in Europe and the time in North America and the starting time in Asia to give you an example of the global presence. So inspired by today's global presence, I'm also wearing green to honor St. Patrick's Day. So I'm going to start sharing the slides here. Are you seeing okay, Dave?
Yeah, you might want to put it in full presentation mode, Xiaosong.
Well, in my computer is already full presentation. Is that yet?
It does not appear in full presentation mode just
Okay.
yet.
Do it again. Do it again. Okay. Sorry.
Yeah.
Should be okay. Okay. Now I'm going to say slideshow. Slideshow,
Yeah,
right?
The button at the bottom. It's not in full presentation mode.
Interesting.
Yeah, no.
I'm going to do it one more time. If not, we might
Okay.
have to stay in the
Yeah.
PowerPoint slides.
Mm-hmm.
I'm not sure why it's not showing the slideshow.
Yeah, not sure.
Now
there
should
you
be
go.
okay. Yeah.
Yes, excellent.
All right.
Yep.
2 times is a charm. So
there you go. It looks good now.
Okay, great. So now it's already afternoon in Friday afternoon in Europe, Friday evening in Asia. So I'm not going to overwhelm everybody with many slides. Rather, I'm going to keep it concise and to the point. And along the way, let us have some fun going through the story of optical fiber and more specifically optical fiber coatings. So everybody, as you know, we are aware the current modern optical fiber, it has a glass cladding in the middle. There was also a small core, which I did not show here, just to keep it simple. But there are also 2 layers of coatings. The first layer is called primary coating. The second layer called secondary coating, right? However, just like in many things in life, we should not take this for granted, because if you look at the history of how the optical fibers came about, in 1970, the very first low loss optical fiber was invented. So that is 53 years ago, 1970. At that time, on top of the glass cladding, there's only 1 layer of coating, a single layer coating system. So 5 years later, there was a breakthrough in 1975. It was reported that a dual layer coating system could significantly reduce microbending. So you remember the low loss fiber? So there is a significant advancement over the 50 years. So there's a relentless pursuit of a lower and a lower loss, part of a loss coming from microbending loss. So after 1975, that is when the current 125, 250 micron configuration took the mainstream, which means 125 micron in diameter for the glass cladding and 250 micron micrometer for the overall coated optical fiber, including both primary coating and secondary coating. So the 125-250 mainstream configuration did not start from day one. It only started after 1975, after a theoretical hypothesis was proposed and people put into practice. So fast move, so remember this, is 125-250 micron configuration is a mainstream for the vast majority of coated optical fibers. Fast forward to around 2000, that is when a reduced fiber size called 200 micron fiber came about. So that is called 200 micron fiber, which actually means we are going to still have 125 micron in the glass cladding size, but we're going to reduce the overall coating thickness. So the overall outer diameter of the coated optic fiber is only 200 micron versus 250 for last many years and a few decades. The reason is for high density cable, we want to fit more fibers in the same size of a cable, because in a lot of big cities, we have limited space to put a cable in the ground. So in the very recent years, around 2020, which is the last 5 years or so, even another configuration was proposed, and certain corporations was able to even produce commercial volume of something called 160 micron fibers, which means the glass cladding is reduced from 125 to 80 micron, and overall coated optic fiber is only 160 micron. So you can imagine, with the given space in the cable, we can fit more such dramatically reduced size fibers into the same cable space. This gives you a very brief overview of the optical fiber evolution in terms of coating, because there are many ways of looking back in the last 50 years to see what happened. It is an amazing journey that the community get together to solve all the challenges to move the industry, to move this optical fiber as a telecommunication media, which is amazing history. This is a very brief, but also focused on the coating configuration point of view. So with this change, what is concerning, which is always concerning and always a greater interest for improvement, has always been microbending. The reason is this is a schematic representation taken from a publicly available in the lightwaveonline.com website about what is the principle of microbending. It is actually pretty simple, because this is a illustration of a fiber, optic fiber, coated optic fiber. Any physical irregularities on the surface in contact with the fiber could perturb the fiber into small radius bands that can cause microbending. So the focus here today is not in all the physics that to calculate microbending or predict microbending. The focus here is we need to realize in reality what could cause microbending are the fiber to fiber interaction and the fiber to cable material interaction in our industry, right? So we just need to remember this, okay? This is the microbending fundamentals. So now go back to that configuration I just talked about. So you have glass cladding, then you have primary coating, secondary coating, right? So the soft primary coating serves as a cushion to absorb all the forces coming from different source, right? Lateral force, right? So the primary coating is a cushion to absorb all those forces so that any forces can be transmitted into the fiber could be reduced. Therefore, it is natural to reduce primary coating's Young's modulus, so that the cushioning effect is becoming greater and greater for more modern and more challenging fiber configuration in the modern days. So let's look at the evolution of primary coating Young's modulus over years, along with optical fiber evolution. Remember the 1975 paper? In that paper, what is reported, Young's modulus of 100 of the primary coating was 100 megapascal. So that is the primary coating Young's modulus level in the 1975 paper. Now, when people realize the benefit of dual coating configuration, the primary coating Young's modulus decreased dramatically. Even in a few years, in the 1980s, it has already reduced from 100 megapascal to somewhere between 2 and 3 megapascal. That's in 1980s. In 1990s, the primary coating Young's modulus was further reduced to only above 1 megapascal. Then in 2000, about 20 years ago, the primary coating Young's modulus has been reduced to slightly below 1 megapascal. So again, our focus here is not the exact number or exact value of the Young's modulus of primary coating. The focus here is to give you an idea of the reason, of the rationale of why we would prefer a soft primary coating for the benefit of microbending, for the low loss fiber, because also for the modern optical fiber network, right? For example, the 5G network, it is more and more demanding for a low loss fiber. And what the coating can contribute, especially primary coating, is to have a soft primary coating with a low Young's modulus to help reduce the microbending loss. So now comes with the first highlight of this paper, of the current innovation. This is the first highlight. Remember, the modulus reduced from 100 megapascal to below 1, which means 100 times reduction in about 25-30 years. So now I want to present the latest innovation that we have developed. So in the current, there was commercial materials from Covestro that has a in situ modulus, which is slightly different than Young's modulus. So Young's modulus was measured on the cured film. In situ modulus was measured on fiber directly. So this is a true primary coating modulus. It's called the in situ modulus. It has a certain correlation with Young's modulus. So anyway, so we're talking about the in situ on fiber modulus. Current coating material about 0.5, so 0.49 megapascal. The next generation coating, primarily for reducing microbending purpose, was reduced to 0.16 or 0.15 megapascal. These two numbers are of the same coating on the different fiber samples from a customer trial, and 0.16, 0.15, very close. So we're talking about a 70% reduction in situ modulus, right? So remember, this is one key point for the highlight. We were able to reduce the in situ modulus about 70%. However, just like with all the any changes, there comes with risk. So in 2006, we presented a paper in IWCS about the risk coming with a very soft primary coating, because in material science, the material strength goes hand in hand with the mechanical property. For example, Young's modulus, which means when we reduce Young's modulus gradually over time, there's a risk of losing strength. For example, in certain, we have observed some kind of tear or rupture in cured primary coating. This is a microscope picture of a primary coat of a microscope picture of a coated optical fiber. So this is the glass cladding, then primary coating layer, secondary coating layer. So we observed a tear or rupture in primary coating layer, because if the coating is not formulated properly, it could, with the reduction of modulus, which is a mechanical property, the strength could suffer. When the strength reduces with the mechanical property, a tear or rupture could be a result. So this is a risk, a natural, in the material science, it makes sense. It's a risk coming with a reduced modulus material, any material, including the primary coating on top of the optical fiber. So now comes with the highlights of today's innovation that we want to share with our customers here is the way we measure the strength of the cured primary coating is to utilize a well-known industry method called tail strength. So the tail strength is measured by loading a cured film on a tensile machine. In this case, is on a DMA machine, right? You load a cured primary coating film. Then next, we make a cut, a well-designed cut according to the ASTM method of tail strength in the middle of the cured film. Then we will pull the cured film apart to measure the force at the time when the film breaks, when this crack propagates to breaking point. The force is recorded and tail strength is calculated in terms of a term called G0. So again, when the focus here is not to talk about how to calculate G0, the focus here is with this well-defined method by ASTM, we measured the cured primary coating tail strength of both current coating, remember current coating, and next generation coating. And tail strength actually increased from 13 joule per meter square to 21 joule per meter square, which is 60% increase in tail strength. So now this is the very first highlight I want to reiterate. So we have dual coating, next generation coating system has 70% reduction in modulus, 70%, 70. But remarkably, it has a 60% increase in tail strength. Therefore, the highlight for this current innovation is the next generation coating system has been reformulated to buck the trend so that while the in situ modulus decreases, the tail strength actually increases, because we realize the risk with the reduced modulus material. Therefore, we have to reformulate the material so that the strength will not reduce, and in this case, actually the strength increases as measured by tail strength. So now we took care of the tail strength concern. I'm going to stop the show. Hopefully you can see my video. Can you see my video, Dave?
Yes, we can see it.
Okay, so before I'm talking about the second highlights, which is the microbending, I just want to also give us a little bit of break, without looking at these slides. So what we're looking at is a one of the cable I got from the laboratory. This cable has a lot of loose tube fibers in the middle of the cable. So in terms of microbending, there's a lot of methods and people trying to simulate and measure the microbending. The challenge is how do we simulate the real world scenarios or situation in actual cable? As you can see, there are many strings of fibers in this particular cable, which is a loose tube cable configuration. It could be also ribbon, but so there's a lot of cable-to-cable interaction, which I also mentioned in the previous slides of microbending fundamentals, right? So now I'm going to put it back to the slideshow here, is that there are 4 official test methods by IEC technical recommendation 62221 ABCD. You know, they use different drum size, even some use even wire mesh or a sandpaper to create lateral force. However, there's one method called method D, which utilizes a basket weave, which means you can wind the fibers in a way that just like a basket weave. So to create a fiber-to-fiber interaction to simulate. So this is actually in our actual laboratory here in our lab to wind the fibers according to all the parameters that was in method D of the IEC technical recommendation, right? It has a well-defined pitch, well-defined take-ups, tension, and layer by layer. So the next layer has different winding direction to intentionally create those cross fiber points that simulate the fiber-fiber configuration, the fiber-fiber interaction that could cause microbending loss. So this is the key why we picked method D among the 4 methods. In this particular paper and innovation, we also intentionally conducted the microbending test with method D. On top of method D, we also performed the test in a temperature cycling fashion, because we realize not only the microbending, but the more specifically low temperature microbending, it is more essential to winter month performance of the optical network when fibers is in the cable. I'm giving you, this is one of the actual microbending test results of the next generation coating versus the current coating. Specifically, the coatings was coated on a 200 micron fiber. Remember, that's 125 glass cladding size and the 200 micron overall coated optical fiber diameter. So let's look at the details of the test. The temperature was color-coded green, which means the cycle starts when the temperature was 25 degrees C, which is ambient temperature. Then we will gradually reduce the temperature to all the way to minus 40 degrees C over about 1 hour, to minus 40 degrees C. Then the fiber will be kept at minus 40 degrees C for about 1 hour again, 60 minutes. Then we will gradually ramp up the temperature. It was done in this cycle, but in this period, will be ramped up from minus 40 back to 25 C. So the cycle is from 25 to minus 40 to 25 again. So this is one cycle, right? One cycle. Then the cycle starts again and again. So in this case, the cycle was repeated 3 times, and the actual attenuation was measured by a LTDR machine. What is shown here, it is not the absolute value of attenuation. Actually, is the change in attenuation. It measures the changes in attenuation starting from the beginning of the cycle. So through the overall the complete cycle, what is shown here is the maximum change in the whole process. As you can see, because when the temperature goes down, when the TG goes down, the material will transition from a pure rubber state to a glassy state. So the modulus of primary coating will gradually increase. As a result, the microbending will, the attenuation will go up as a result of microbending loss. So as you can, for example, in this case, was measured at a 1310 nanometer wavelength. The one in blue here is this curve is the current coating. It has about 0.03 kilometer dB per kilometer loss, and here down here much less reduced attenuation in change is the next generation coating. There are two fiber samples. They're more or less the same, right? The 3 cycles, the maximum change in current coating also reduced because of relaxation. But give you idea of a much reduced microbending in the next generation coating system because of the reduced mechanical properties in terms of the modulus. To give you idea of the benefits, the same microbending was also tested at 2 more different wavelengths, 1550. You see the same trend. The next generation coating system has much more reduced the attenuation in change in 5050 than the current coating. However, the absolute value went up because it was well known in the industry that the attenuation loss or attenuation absolute value goes up with the wavelength. And more dramatically in 1625 nanometer, the absolute value went up again, but we still see the same result, same trend, that the next generation coating has a great benefit of reducing microbending loss. To summarize, we only look at the minus 40 degrees C range, the results. We summarized, this is only looking at the minus 40 degrees C, which is these 3 regions, and do average of 3 cycles, then compare the 2 systems, the current system in blue and also in orange, or in the next generation system. So 1310, 1550, 1625 nanometer in the 3 different wavelengths. So you can see it's well known because when the wavelength increases, attenuation value increases, as well as the change in attenuation also increases along with the wavelength. However, if you look at the absolute, the maximum change in attenuation at minus 40 degrees C, 0.02. So for 1310 nanometer, 0.02 for current coating, 0.001 for next generation coating system, 0.07 in 1550 nanometer, 0.07 for the current coating, 0.003 for next generation coating system, and 1625 nanometer, 0.11 dB per kilometer for current coating system, the change in attenuation, while that number is only 0.004 for the next generation coating system. So there's a step change in terms of microbending reduction, right? So now I'm running out of time. So the next part is talking about draw tower simulator results of the 2 coating systems. You can find all the results in the actual IWCS paper that we published last year in October, which is not the highlight of the current paper. The 2 highlights of the 2 current paper is a improved tail strength, which I have talked about in the previous slides. With the reduced incision modulus, we were able to improve the bucket trend, improve the tail strength, as well as a greatly reduced microbending level in a very challenging 200 micron fiber configuration. So these are 2 highlights. I'm going to skip the draw tower simulator results, which you can find all the details in the actual paper. I'm going to jump into the final conclusion, which I say, it's already Friday afternoon, Friday evening in Europe, in Asia. So all you have to remember is as simple as 1, 2, 3. So you remember 1, 2, 3. So what is 1? 1 is we have developed a next generation coating system, which is a family. So this is not a single coating. It's a family of next generation primary coating systems, coatings, which we can tailor make for various customers, depending on customer needs. So what are the 2? So as simple as 1, 2, 3. 2 is there are 2 benefits or 2 improvements. The first improvement or benefits is an improved tail strength. So 60% improved tail strength over the current system, while the in situ modulus was reduced by 70%. The second improvement or benefits is a superior low temperature, which is minus 40 degrees C in this case, low temperature microbending resistance, particularly at high wavelength, specifically 1625 wavelength. So what is 3? 3 is there are also 3 draw process capabilities. So we have not forgotten that the fiber has to be able to be manufactured under the modern manufacturing conditions. For example, super high draw speed, as high as 3,000 meters per minute and even beyond. The second aspect, helium consumption rate optimization or reduction. And the third, it has to be hybridly cure capable, which means it can be cured with the traditional microwave UV lamp, as well as the upcoming UVLED lamps, as many customers are transitioning into UVLED lamps. So all those coatings, these new generation coatings, are UVLED curable. So there are 3 robust draw process capabilities. By the way, all those 3 capabilities have been published in the recent IWCS papers. So you can find the detailed description of the specific respective innovations in recently published IWCS papers. So to take home, all you have to remember is 1, 2, 3. 1 family of coatings, 2 benefits, 2 improvements, and 3 robust draw process capabilities. So with that, I would like to thank you for your attention, and we are going to answer a few questions you might have.
Xiaosong, yes, thank you very much. Very interesting. It was a very, very good history lesson. I didn't expect that. So again, we thank you so much for your time and consideration to help educate us. There are a few questions. If anyone has any last minute questions, please enter them in the chat function, and we'll try to address them as quickly as we can. Xiaosong, what is the minimum and maximum thickness of the color coding?
So I want to make sure I understand. Are you talking about a ink system or ink or something else?
Yes, I assume so. I mean, it's just the color layer, I guess, is what, is there an actual layer, or is it just an embedded?
Yeah, so
amount?
Correct. Yes, it's a very good question. So this particular paper only addresses the primary coating, especially primary coating of a natural fiber. So I don't remember exactly what color or the ink was on that 200 micron fiber. It could be also a natural color, because in the actual 12 color fiber, there was 1 fiber that might not be even colored. But anyway, I don't have an answer of exact maximum or minimum. I think traditionally it's between 5 to 8 micron thickness of the inking layer, but I could be wrong. I'm not expert in the inking of the inks. So
I mean, that
Fuchs,
seems like a good estimate, though. In
5
terms
to
of
8
the
microns.
research. Yeah,
Yes.
I think that's good. How do you make sure it's microbend and not macrobend from the routing?
Yes,
Yeah.
very good question. Remember the one slide that had the microbending fundamentals in the Lightwave website? It actually has 2 parts. And the first part is talk about macrobending. And the second part is microbending. And it was actually the microbending, which is part 2, that the coating can contribute significantly. The coating cannot do much about macrobending, which
Okay.
is a fiber. The fiber. There's a lot of innovation of the optical fiber itself to define even the refractive index, for example, refractive index configuration in the core, right? So this is a different topic, but there are many published IWCS papers about the innovation in the fibers, which can contribute to a lot about microbending performance. But as you can see in this particular paper, because coatings can only help with microbending loss, that's why we focus on microbending test. And actually, this technical recommendation 62221 is specifically addressing microbending loss, not macrobending loss.
Very good. How about aging, high temperature aging, and the influence on the coatings? Is it possible to use at an operating temperature of 105 degrees C?
Okay, very good question again. As you can imagine, this vast majority of the optical fiber, the application was to deploy under the ground or under the sea, right, for submarine cables. So the temperature range is a ambient temperature to winter months, between winter months and summer months. So anything above like certain temperature, like 105 degrees C, goes to high temperature applications, right? So what I'm trying to say is, for the vast majority of telecommunication applications, there are a certain temperature range, right? So the data I'm presented here, the coating was not designed for high temperature application. However, the same principle can be applied to developing high temperature coating systems. And actually, Covestro do have different product lines, product portfolio for various specialty coating applications, including high temperature. But coming back, the data I'm presenting today was for the vast majority telecommunication applications, which was not designed for high temperature application.
Very good. New generation coatings will be more important, obviously, for microsensitive 80 and 160 micron fibers. Which network will this smaller fiber be used in the future?
Yes, this is beyond my knowledge. I do, so last year, October, when I went to Providence, it was fascinating in the high density cable session. It was fascinating from quite a few customers where they're showcasing their 80, 160 micron fibers, which was unimaginable in the old days, right? When you have 125, 250, which was like people take it for granted, me also included, take it for granted, going all the way to 80, 160 micron, which is phenomenal advancement. I'm sure that these fibers will find their way into very challenging network construction, hopefully for help us for the future modern networks.
Good.
But I don't have an answer for that question. Sorry.
I mean, it's all new, and who knows where we end up with some of these technologies. It's pretty impressive. Can the material be used for recoating or applied to fiber-based devices?
Again, so this is also beyond my expert, area. I am sure that for a specific, if the devices, for example, optical devices, if the microbending performance would benefit in some way, that could be utilized. However, we might have to reformulate specifically for that customer curing conditions. So it might not be drop-in, it might not be like off shelf. It might have to be, we have to take into voice of customer consideration. But generally speaking, if microbending is of importance for that application on those optical devices, yes, the general principle will apply in this case.
Very good. And as always, we need to address the environmental concerns and restrictions lists. Are the new generation coatings REACH and RoHS compliant?
That answer is actually yes, because to commercialize this kind of coating system, just like in many other previous generations, regulatory is always one of the requirements we have to meet, and sometimes one of the hurdles we have to overcome. Therefore, these materials are fully REACH compliant, as well as being compliant to many other inventory requirements for many other regions. For example, like North America, Asia, many other different countries in Asia. Yes, so these materials are fully regulatory compliant globally, including REACH for Europe.
Good. All right, just a few more questions. I think you've already answered this question, but we'll go ahead and ask it again. Does this coating system work in the 160 micron fibers?
Very good question, very interesting question. So as you can see, the data actually was on 200 micron fiber. So this new coating has not been coated on an actual 60 or 8160 fiber. It has not been coated. It has not been tested. However, we believe if you compare apples to apples, which means if you put the next generation coating and current coating on the same 8160 micron fiber, you would be able to see a similar microbending loss benefit with the next generation coating system. We believe so, but we haven't done that. We have not made any actual fiber and tested.
Very good. Okay, and last question: is there any change in secondary coatings or only in the primary coatings?
It's a very good question. Actually, this question actually is like reading my mind, because as you can see, because primary coating, secondary coating comes hand in hand. And to generally answer the question, yes, we are also making step change in secondary coating innovations, because you have two considerations. Again, as I said, primary coating, the material has to be able to be processed, which means able to manufacture under modern fiber drawing conditions. So the secondary coating also plays an essential role in the overall system. It's a package. So it's a package, the primary coating, secondary coating package that has to be able to be manufactured under modern draw condition, for example, super high speed. So that's also the same requirement for secondary coating. Second, the secondary coating mechanical property, for example, modulus, also helps with the overall microbending performance. So it's not only primary coating, it has to come with a secondary coating on top of it, right? They come together. So the mechanical property of primary coating as cursion, secondary coating mechanical property as a shield, a very hard secondary coating, together to offer the overall microbending performance of the coated optical fiber. So yes, secondary coating is also very important. We cannot forget about it.
Very good. Okay. I saw a question about your contact points, but again, thank you, Xiaosong, for presenting this very interesting and important topic today. A lot of innovating technologies coming over the near future. And please note the contact points that are now being shown on your screen should you wish to contact Xiaosong after today's event. Xiaosong is very approachable and will be eager to follow up with you directly. You've got his phone number as well as his email address. Each of these webinar series presentation events are recorded and will be archived on the IWCS website. It normally takes a few weeks to have these posted, but it will be up shortly. So feel free to go and watch again, plus all of the other previous interesting webinars that we've archived. I do want to mention again that we are currently accepting abstracts for technical papers for our upcoming conference in September in Orlando, Florida. So our deadline is 3 weeks away, and we hope that you will work with your colleagues in your own companies as well as your supply chain to encourage some good innovations, just like what Xiaosong was presenting. And we would be very interested in continuing to provide these interesting technologies to our global audience. So please enter your abstracts within the next few weeks. This IWCS webinar series conducts both technical papers as well as sponsored company events each month. And our next webinar is scheduled for April 21st at 10:30 a.m. Eastern USA time. We typically try to run these the third Friday of every month. Each of you will be receiving an announcement for the event. So please feel free to share our announcements with your colleagues so they can join and register as well. It's really important that we recognize and thank our IWCS partner sponsors, including Covestro, who greatly contribute to the success of the Cable and Connectivity Industry Forum. Without their strong leadership and generosity, as well as the important technical innovations like you heard today, we would not be able to bring these important technical innovations and information to you and our global community. So again, thank you to these leading suppliers in our industry for your support. Here we go. So again, save the date, September 17th to the 20th in Orlando, Florida at the Gaylord Palms Resort and Convention Center. For over 71 years, the IWCS Cable and Connectivity Industry Forum has been the recognized leader in showcasing new technologies in cable and connectivity products, processing, and applications. So again, our next conference is in September. Please watch your inbox, social media, and also our website to learn more as the exciting information becomes available. Please visit our website, iwcs.org, and you'll be seeing a lot more event details as they come up over the next month or so. So thank you for participating. Enjoy your St. Paddy's Day. Go out and have a libation or two, and have a great weekend. Thanks again. Stay healthy.
Thank you, Dave. Bye.
Thank you, Xiaosong. Excellent presentation.
Bye-bye.
Bye-bye.